Morning, Assalamualaikum. So today we will continue. Okay, we continue on the previous lecture, yesterday's lecture, where we had done on the PTA table, exercise for PTA, heat cascade. Okay, just to recap on yesterday's exercise. Okay, just to recap on yesterday's exercise, once you are given an example or a question where you are given a PFD, okay, PFD. So you should identify the hot and cold stream. What is the delta H? What is the CP? What is the internal temperature? Okay, and the important part also is the delta T min. If you are not given this value, the delta T min, you should ask for it. Or you can assume but justify your assumption. Okay, usually the range will be 5 to 10. Okay. Okay, then calculate CP, delta H, the delta T. Okay. And then you can proceed with the shifted temperature in order to do the table algorithm. Okay, shifted temperature, hot minus the delta T min over 2, cold delta T min plus, plus delta T min over 2. Okay. Okay, construct this table where you should list down all the interval temperature in sequence. Descending order. Yeah, descending order. Then draw the stream population for the hot and cold stream. Okay, make sure you drag the TS and TT correctly. Okay, then find out the delta T interval for each interval, for each zone. Okay, find the delta T and also the total CP. CPC minus CP hot. Okay, notice and be aware of the sign, plus, minus. Then calculate the delta H, where the delta H is calculated from CP multiplied with delta T. Okay, CP multiplied with delta T. From there, identify whether it is surplus and deficit. Okay, so if you are required to construct this table algorithm, all these infos should be included. Okay, until the identification of surplus and deficit. Okay. Then after these values are completed, then only proceed with your heat cascade. Okay, the first heat cascade always assume 0. First heat cascade always assume 0. Okay, the purpose of the first heat cascade is to find your hot utility. How much is your hot utility? Hot utility is the lowest negative value. Okay, that is your hot utility. Now, taking that hot utility, create the second cascade. Okay, using the hot utility, create the second cascade, find until you get 0. Okay, the 0 megawatt is your pinch point. Pinch point, not yet the pinch temperature for hot and cold. Okay, pinch point. So taking that temperature at the pinch point, pinch minus delta T min over 2. Cold pinch plus, hot pinch plus delta T min over 2. Cold pinch minus that. So this is your hot pinch temperature and cold pinch temperature. Okay, then and also from the second heat cascade, you can identify your QC min as well. Okay. Now let's say from the composite curve, you can identify QH min, QC min, and Q recovery, right? From the heat cascade, how you can determine the Q recovery? Heat cascade, you have QH min, QC min. How you can identify the Q recovery? That's a question for you to think, how to find out the heat recovery for heat cascade. Again, composite curve and heat cascade, the QH min, QC min should be the same. Okay, any question before I move to the next one? Yesterday's example, any question? All clear? Now for today's part, we want to focus at the above pinch and below pinch. Okay, after you had done the heat cascade and then identify how many heat exchanger that is required, at the end, you should be able to construct this heat exchanger network diagram. Okay, this is the final part to construct the heat exchanger diagram. Okay, how to do that? After we perform the heat cascade yesterday. Okay, this one, it used the previous example, not the yesterday one. The previous example. From this one, this stream, the one for the heat cascade, this is the one. Okay, this is the value for QH min. QH min and QC min. This is from previous example, slide 38. Okay, and then the pinch point at 145 degrees C. Okay, so pinch point at 145 degrees C, meaning that hot pinch, what temperature? Hot pinch, what is the temperature of hot pinch? This one, delta T min is 10. Pinch is 145. Hot pinch, temperature for hot pinch, 150. Okay, 150. Cold pinch, 140. Okay, that's the pinch point. Now then, okay, we divide the diagram into above pinch and below pinch. Identify your pinch point. Hot is 150, cold is 140. Okay, the stream, look at the stream. Stream 2, which is the hot stream, from here to here, 250 to 40. Stream 4, hot stream as well, 200 to 80. it passed through the pinch. Now, cold stream, first stream from 20 to 180. Pass the pinch at 140. Okay. Stream 3 starting at 140 to 230. Starting from the pinch point. Okay, so now above pinch we have 4 streams. Below pinch we have 3 streams. Okay. CP here is from the table that been provided. Delta H, the one that you have calculated earlier in that previous example. Okay. Okay, now. Up to here, can separate above and below pinch. Now we go one by one. Below pinch. Okay, below pinch. This is hot, hot, and cold. Cp remain the same for each stream from the given value. Okay, but delta H over here is not the same. How it get this 16.5? From the table, Cp for the second stream is 0.15. Okay, 0.15. Then the delta H given from the table is 31.5. Yeah, if you're confused what I'm saying. Now, stream 2, this is the Cp, this is the delta H from the table. Now it's split into below pinch and above pinch. Delta H is different now. How it get this new delta H? Correct. Cp multiplied by the delta T. Delta T here is between the pinch and the target. Okay, here 16.5 you get 0.15 multiplied by this delta T. Okay, Cp multiplied by delta T. Delta T here is 150 minus 40. Then you get the 16.5. Okay, same goes for the rest of the stream. Because we divide it at the pinch. So delta T will be different now. Above pinch, same thing. Cp multiplied by delta T. Delta T here is 250 minus 150. Okay. That's how you get all this delta H at this side and also this side. Okay, up to there? Any question? I go step by step so that you can understand. Now, from there, we start design at the pinch, divide above and below pinch. Then we find the Cp inequality. Above pinch, it should be Cph smaller than Cpc. Then only you can do the heat integration above pinch. Cph smaller than Cpc. Okay, above pinch. Below pinch, CPH larger than CPC. This is the rule. Okay, then again you create the CP table. Then tick off the stream that you have complete the heat exchange, the heat integration. Okay, after that, you will know how many of heat exchangers required and the utility capacities. Okay, now we go one by one. Okay, the pinch design method. Now, above pinch, step 2. Step 1, just now, we start at the pinch, divide above pinch and below pinch. Step 2, find the CP inequality for individual match. Okay. The temperature profile for an individual exchanger at the pinch, above pinch. Okay, moving away from the pinch, temperature differences must increase. Above pinch, CPH must be smaller than CPC. Above pinch. Now, look at this stream. This one is above pinch. Stream 2, from 250 to 150. Okay, CP as stated earlier. Now, CPH must be smaller than CPC. Here it shows you CPH 0.25 exchange with CPC. Here CPH is larger than the CPC, which is not feasible. Okay, this is not feasible. 2 and 4 is hot. 1 and 3 is cold. Now, when you see here, stream 4 and stream 3, CPH, CP3, CPC, 0.25 smaller than 0.3. So this one works. Stream 2 and stream 3. Okay, just now 4 and 3. 4 and 3. Now, stream 2 and stream 1. Is it feasible? Stream 2, stream 1. Feasible according to the CP. Stream 2 and stream 1. I'll make it larger. Stream 2 and stream 1. Does it meet the rule? Yes. Stream 2, stream 1. Any more? Stream 1 to stream 3. Feasible? Stream 1 to stream 3. Sorry, stream 2, stream 3. Sorry. Stream 2, stream 3. Feasible, right? CPH smaller than CPC. Up to here again. CPH smaller than CPC. That is above pinch. Now we move to below pinch. CPH larger than CPC. Must be larger than CPC. So here are the pinch. Below pinch, we have only 3 streams. Hot, hot, and cold. H must be larger than cold. Okay, so here 2 to 1 not feasible. Okay, 2 to 1 is not feasible because CPH smaller than CPC. Stream 4 to stream 1 feasible. H larger than C. Equal. Can? Larger or equal? The sign. Larger or equal? Okay, I repeat, larger or equal, smaller or equal. So below pinch, CPH larger or equal to CPC. Okay. Can I up to that? Now, step 3 is the CP table. CP table for design above and below pinch. Listed in descending order. Okay, in descending order. Okay, this is above pinch. CPH smaller or equal to CPC. Okay, CP in descending order. Arrange them in descending order. Above pinch. Same thing for below pinch. One is hot, hot, cold, cold. Okay, so from here we can see larger, smaller for above pinch and larger for below pinch. Okay. Okay. Now next step. Step 4, to tick off the heuristic. Now, minimum number of heat exchanger unit leads to reduced capital cost. So we must find the minimum number of heat exchanger. Okay. Now, above pinch. Focus on above pinch. CP hot must be small or larger than CPC, above pinch. Larger or smaller? Above. Hot must be smaller. CPC. Okay. Okay, now. Just now, we had decided that stream 2 smaller with stream 2 and stream 1 feasible, stream 4 and stream 3 feasible. Okay, now remember the delta H that you calculated earlier, the above pinch. Okay, this one, delta H. Okay, take note on this, delta H above and below. Okay, take note of this. Now, according to that, this one above pinch. So just now delta H for this is 16.5, 17.5. I just copy back. Sorry. I'm mistake with below pinch. Sorry. Now above pinch, this one should be 15, 12.5, 8, 27. Okay. Okay. Hot stream give out the heat to cold stream. So stream 2 give out the heat to stream 1. How do we know how much heat to be given away? How much delta H to be given away? So we see at the delta H for each stream. Stream 1, it requires 8 in order to achieve the T target. Okay, it requires 8. So stream 2 will give only 8 megawatt. Okay, stream 2 will give out only 8 megawatt to stream 1. Okay. Yeah. So stream 1 done. We had transferred the heat and it achieved the target temperature. Take off. Okay, take off the stream. Stream 4 give out the heat to stream 3. Where stream 3, it requires 27 megawatt to achieve the T target. Okay, but stream 4 have only 12.5 to give out. Yeah, yes, stream 4 have only 12.5 megawatt to give out. But stream 3, it required 27 megawatt to achieve the target temperature. Now, stream 4 give out 12.5 only. Stream 3 receive only 12.5. So the T target is not achieved yet. It only achieved up to 181 degrees C. The T target here should be stream 3, 230. This is the T target. So by receiving the 12.5 megawatt, it only hit up stream 3 to 181.7. How do we get this temperature later? Okay, now I want to explain how the heat being transferred. Okay, up to there, can? Okay, so stream 4 tick off has been used up. Okay, it already passed down all the delta H. So stream 4 and stream 1 settle. Okay, now Stream 2. Total is 15. It already gives out 8. So remaining of stream 2, it gives out 8. Change the temperature to 203. Okay, this one it gives out 8. So it changed temperature to here. Okay, it still have 7 megawatt left. Total is 15. So left out 7. So it gives out that 7 megawatt to stream 3. Here, stream 3. Okay, 7 megawatt. Just now, the initial part, it gives out 8 megawatt to stream 1. Stream 3 still not sufficient, the delta H. So it get the delta H from stream 2. Okay, so stream 2 pass to stream 3, the remaining delta H, 7 megawatt. Change temperature in stream 3 from 181 to 205 only. Still not meeting the T target because it requires 27 megawatt. Now you have only 19.5. Okay. Stream 2 now, finish up. Already finished. So tick off. Okay, so here, this one, the middle part one, it seems like the 3 streams over here have given out the heat and received the sufficient amount. Stream 2 and 4 given out all the heat. Stream 1 already received sufficient. Just left stream 3. Okay, so the remaining 27 minus 19, what you get? 27 minus 19.5. 7.5. Okay, so this 7.5 is the one you need to supply your hot utility. So now stream 3 has enough 27 megawatt in order to achieve the T target, 230. Yes. Stream 1. How do we know must give stream 1 8 megawatt? Okay. Now, I start from beginning. Here, hot and cold. Hot, hot, cold, cold. Okay. Above pinch, CPH must be smaller or same as CPC. Okay. Now, 0.15 smaller than 0.2. Right? so they can integrate. Heat can be given out. So how do we know 8? Because stream 1 requires 8 megawatt. Stream 1 requires 8 megawatt to achieve the T target. So stream 2 pass down only 8 megawatt. How do we know here is 8 megawatt? Delta H 8 megawatt. What? CP, yes, correct. Okay, that's how you know 8. The delta H is 8 here. Required for TS to TT. Yeah. Okay, any more questions? You must understand this part first before I explain to you the temperature different. How to get the temperature different. Sorry, how to get this temperature. Not the T target. Okay, up to that? That one is above pinch. Please ask question if you need to repeat. If you need me to repeat. I can repeat, no problem. So, above pinch now is completed. We identify 7.5 is to be supplied from the hot utility. Now, from here, how many heat exchanger? 4. 4 heat exchanger. Right? 4. Heat. Okay, 1 heater. Here it exchange the heat between the stream. Okay, the line here is the heat exchange. Heat integration between the streams plus 1 heater. Okay, now this is above pinch. Similar approach for below pinch. Below pinch, CP hot larger or same as CPC. Okay, so 2-4 is hot. Only 1 cold stream. Stream 4 can be transferred to stream 1 because it fulfills the requirement. Okay, and then the delta H just now from the earlier calculation, 16.5, 17.5, here is 24. Okay, this is the delta H from earlier calculation. So, stream 4 transferred 17.5, fully 17.5, because stream 1 requires 24 megawatt to achieve the T target. Why stream 4 transferred 17.5? Because that is the only amount it has. So it gives away everything to stream 1. Okay, give out everything to stream 1. So we tick off stream 4. Stream 4 is fully used. Now, stream 1 is not enough heat yet to meet the T target. "24 is the required. Now we have 17.5. So you still need how many to achieve the target for stream 1? How many? 6.5 for you to achieve the T target for stream 1. Okay, stream 1. So this much of energy is required. So where we can get? We can get from stream 2. Stream 2 still fulfilling, stream 2 CP hot, CP hot is smaller than CPC. Right, stream 2, the CP is smaller than CPC, is it? Okay. Okay, let me clarify on this later. I'll try to check because CP2 is smaller than CP. CP for 2 smaller than CP for 1. But here it shows it transferred the energy by 6.5 megawatt. Okay. Later I'll clarify this one with you. Okay, for now we check on the transferring first. Now CP2 transferred 6.5 more. So stream 1 now is equal to 24 megawatt. Fully transferred. So stream 2, since it transferred the 6.5, now stream 2 remaining minus 6.5, so remains 10 megawatt. Okay, so it needs 10 megawatt to cool down stream 2 to T target 40. Okay, so that's why here it install cooler with 10 megawatt. Okay, so now you have two integration, heat integration, stream 4 to stream 1, stream 2 to stream 1. Then add on with one cooler. So stream 2 now, you have enough delta H. Okay, so you have met your T target. Okay, up to that? Okay, I repeat, for stream 2 just now, 16.5 minus 6.5, which it passed through stream 1. It has remaining of 10 megawatt. So 10 megawatt here, the stream need to be cooled down. So that's why here it install cooling, cooler. Need cold utility to achieve the T target. So now all stream tick off. All meet the requirement. Okay, so from below pinch, we had identified minimum cooling utility, QC min. Okay, any question? Okay, this is the summary of the below pinch with one full utility. Final heat integration network, it should look like this. Okay, a complete network. So 2, 4 is the hot stream. Okay, hot, hot, cold, cold. Okay, so from here, how many heat exchanger involved? From this network, how many heat exchanger involved? Inclusive the cold, the cooler and heater. 7. Okay, 7. How we get 7? 1 for here. 1, 2, 3, 4, 5, 6, 7. 5 heat exchanger. Sorry, 7 heat exchanger, sorry. Okay, this is the complete network. So once you get the complete network, you are required to construct the final heat exchanger network. So it will look like this. Okay, how to connect this? You should relate back to the stream feed info. Yeah, stream 1, feed 1. Okay, let's try. Feed 1 last time is feed 1 is from 20 to 180. 20 to 180, stream 1. Stream 1 here, stream 1. Stream 1. Yeah, stream 1. Okay, which from the network over here? This one. Okay, stream 1, feed 1. Wait, I'll make it smaller so that you can see. Okay, stream 1 over here from the network, and here is feed 1. Stream 1. Okay, the T supply is from the feed. T target is the one that entering the reactor. Okay, from the network, there are 3 heat exchangers involved. Okay, this one, this, and this, which connect with stream 2, stream 4, and again stream 2. Okay, so here you see this. One, 2, 3 heat exchanger. Okay, so you go back, you relate back with the diagram, the complete heat exchanger network diagram. This one is the after integration, after heat integration. So your after heat integration PFD should looks like this, involving the heat exchanger. Yeah, which the original PFD before the heat exchanger last time, yeah, just to share with you. That is slide 16. This one. Yeah, yeah. What is it? Okay. This is the before heat integration. Before heat integration. Yes. You have question, Jason? How do you arrange means?
Is how do we find the minimum number of exceptions?
The sequence. The sequence. The minimum just now we had did. Minimum heat exchanger. The above pinch, below pinch. That is the amount of heat exchanger. The sequence, you mean this one, 1, 2, 3. How to arrange? based on the network just now? Okay, based on this network, as long as you have, okay, stream, we focus on feed one only, yeah? You have 3 heat exchanger, right? You have 3 heat exchanger over here. So the sequence, which one come first, it depends how you arrange your stream. Yeah, as long as it meets the requirement. You have T target, T supply, T target, right? Yes, when you pass through one heat exchanger, you have new temperature.
What if our CPH is greater than CPC throughout the whole process?
First thing, is there a pinch point?
Why there's no pinch point? Make some correction.
If no pinch point, then you cannot do the above pinch and below pinch analysis. There are heat integration between hot and cold. I mean, maybe heat recovery area, right? Heat recovery area. But pinch, you need to find out. Is there any pinch point exist over there?
Why if I design in such a way there's no pinch point? Can I just skip the whole heat integration chapter?
Justify.
No pinch point.
Justify. But the heat integration, the heat exchange is possible. You see just now, below pinch, above pinch, there are categories. So you fall in which categories? Justify. Justify. The process is the same concept. Okay, heat exchange between hot and cold. That's the main thing. Try to figure out. Okay, now I want to share with you just now the temperature difference. You see, here we take below pinch. Let's see, below pinch as example. See my notes. Okay, below pinch as an example. Now, how do you know what is the temperature? What is the new temperature after you install the heat exchanger? Okay, listen. Listen. Now, the first heat exchanger for stream 1, it supplies 17.5. Okay, which not meeting the requirement. So not meeting the T target yet. Now, how to know it reached until what temperature? How to know with this 17.5, it reached up to what temperature? Your target for stream 1 is 140. I'm sorry, below pinch. Okay, so your target is here. Now, how do you get this 52.5? I'm asking question over here. How do you get this 52.5 degrees C? After you install your first heat exchanger. How do you know it is 52.5, not 50, not 100? Stream 1 from 20 to T target is below pinch, 140. How do you know? You see, when you install the second heat integration, then only you get your T target. How do you get the 52.5? Huh? Correct. Then T final, T initial. So this is your unknown. Okay, correct. This temperature is unknown. You only know the delta H that being transferred. Okay, the delta H that being transferred. So we know that delta T is equivalent to delta H over Cp. Okay, so delta H now 17.5. Sorry, 17.5. Cp is 0.2. You will get the delta T. So delta T here, your final target is 140. Okay, so 140 minus delta T here later you will get 87.5. That is delta T. So to find this unknown, find out. This is your delta T. So to find the unknown, minus 140 minus this. Okay, this is delta T. So to find your T unknown over here is 140 minus 87.5. Then you get the 52.5 degrees C. You can do the same once you transfer 6.5 over here, whether you get 20 or not. Okay, you can do your part. Okay. One last The last slide. So the summary you can read on your own. Okay, the number of heat exchanger unit. Minimum number of heat exchangers. So this is the formula. Number of heat exchanger. The S here, streams, including the utilities. Okay, so stream here, we have above pinch and below pinch. At stream above pinch, which is 1, 2, 3, 4, including the utilities. So 5. So you get 5, huh? 1, 2, 3, 4, 5 stream. Minus 1. Plus below pinch, 4 stream, including the utilities. Okay, so from this calculation, 7. Meet with your heat exchanger network earlier. Okay, so from this calculation, it meets the network. Okay, so here it shows the 7 proof with this calculation. What?
Most of the time, they only buy one quality.
It depends to your stream. And also it depends to your cooler capacity. Means that cooler able to supply how much of energy. For example, let's say that cooler, the pack given by the manufacturer, it can supply only 5 megawatt, for example lah. So here you need 10 megawatt. So means you need 2 cooler, right? I pray for you. Okay. Any questions? So we are done with chapter 4.
The experience liquid and polymer together is 7 right?
Separately. Liquid, heat required by the liquid, then heat by the vapor. For the for some info, some of your PDP project lah, when it involve phase change, so the delta H phase change CP different. So you have to do liquid up to the boiling point, for example lah, liquid to vapor, right? So liquid temperature to the boiling point, heat of vaporization, then the boiling point to the heat target, the T target.
That one is based on pure component. Our pure
Have
components.
to do lah. Have to do lah.
the basis of this pure, but
No choice, have to do.
it's assumed that same activity, then you just assume same about it, and you know,
So one thing like if one phase change from liquid to vapor, right? So liquid to the point one is exchanger, then phase change one is exchanger, then vapor one is exchanger.
it's what is all my reactors sometimes.
No, no. Because it is the heat accumulation of all. Let's say stream, right? Involve phase change, so the accumulation of the heat released by that stream.
Okay.
Okay? Anything else? Okay, we have done chapter 4. For the rest of the slide, I'm not sure whether yours have this exercise, huh? Have, huh? Have. Because I have 2 set of slide. I'm not sure with the which one. Okay, please try to do this exercise so that you can understand better. Okay, my advice, do this exercise for your test. Yes. Sub question. Maybe 2 main question. Sub. Possible? Okay. I would suggest you to do the exercise. Then the rest of the slide you can just read through. Okay. So next week I will start chapter 5. Just have a look on the notes so that you have some idea on what we are going to learn. Okay, so that's all. Thank you.